Alright, time for another probably lengthy exercise. So let's get started. So we're going to talk about the interior. And so the interior consists of all interior points of a set, obviously. So um, let's see here. Let's just jump right in and prove that the interior is always open. So let's see here. For each element in the interior, well, if x is in the interior, then x is an interior point for E, which means by definition, there is a neighborhood NRX of x. So a neighborhood consisting of all points whose distance from x is at most r. No, strictly less than r. There's a neighborhood of x, which is entirely contained in E. Okay, so let y be an element of NRX and so let's say that this is an element of this neighborhood which is not equal to x. So this is NRX, we remove x, and we're also going to let delta be the minimum of the distance between x and y and r minus the distance between x and y. So what's going on here? So this is a case where it's good to draw a picture to show what's going on. So we have this this point x here and this point y, and we've got this ray which goes from x to the boundary of NRX. And so this entire ray here has length r. And this, of course, is the distance between x and y. And if this is the distance between x and y, and this entire ray has length r, then this part, the length of this line segment must be r minus the distance between x and y. So what delta is delta is the delta is the smaller of these two segments. So what we're going to do is we're going to use delta to construct a ball, a neighborhood of y, which is entirely contained in E. And so what we're going to do is we can say then that n of delta, a neighborhood of radius delta over 2 centered at y is obviously a neighborhood of y, and it's contained entirely in NRX. And thus, well, it's contained in NRX, which is contained in E. Obviously, because it's a neighborhood. This implies y is in E. Y is in the interior of E, because we can surround y in a neighborhood which is entirely contained in E, and that's what it means to be an interior point. So y is an interior point of E, meaning that y is in the interior of E. This holds for every single element y in NRX, set minus x, and thus, combined with the fact that x obviously is an element of the interior of E, it means that the entire neighborhood NRX is contained in the interior of E. And this holds for... Okay. This holds for everything. Okay. Alright, so now, denote by nx a neighborhood of x contained in, see here, contained in E, which is thus contained in the interior of E. Then, what do we have? Well, E, so every element of E has a neighborhood which is entirely contained in E. And so what we can do is we can write E, the interior of E is contained in the union over all x in the interior of E of this neighborhood nx. Because obviously each element of E naught belongs to the corresponding neighborhood, and so we have this inclusion. But now this is a union of elements in E, this is a union of elements in the interior of E. And since it's a union of elements in the interior of E, this union must be in the interior of E. Okay, so we have the interior of E is contained in something which is contained in the interior of E. Thus, the inclusions are actually equalities. And so the interior of E is the union of over all x in E, over all x in the interior of nx, which is a union of open sets. And what do we know about unions of open sets? They're open. And thus is open. Or we can say and hence is open, because that's what we want to prove. We want to prove that E interior is open. This is really nice. I really like proofs like this, where you have like inclusions going one way, and you just have this is included in this, and that's included in this, and you keep going, and you get to where you started, and then you're able to say that these inclusions are actually equalities. Another thing that's similar to this that you see in some proofs is you'll see something is less than or equal to something else, which is less than or equal to something else, and you keep doing these inequalities, and you'll eventually get back to what you started with. And then those inequalities become equalities. Proofs like that are super nice. If you go on after this and read Fallen et al., this is basically how Lebesgue-dominated convergence theorem goes. You have a whole bunch of inequalities, and you get back where you started, and so you're able to turn them into equalities. It's really nice. I don't know. Okay, so we have what we wanted. And so now we're going to move on to part B, which I have, I actually wrote down everything here so that I can remind myself and remind you of what it is, because it's not on screen. So part B is prove that E is open if and only if E interior equals E. Okay, so one direction is easy. If E interior equals E, then E is open since E interior is. And E interior is open because of part A. If E is open, then each element of E is an interior point. Remember, that's how we defined open sets in the first place. The whole open sets being unions of open sets, that came later. Here in this textbook, we define open sets to be sets in which every element is an interior point. So every element of E is an interior point of E, and thus belongs to E interior, because it's an interior point. And the interior of E is defined to be the set of interior points. Okay. Thus, we have every element of E is in E interior, so we have E is contained in E interior. And this combined with the fact that E interior is contained in E, and that's because E interior is a subset of E. It's a set of elements in E which also satisfy another property. The other property being that they're interior points. But anyways, so this inclusion always holds, and this combined with this yields E is actually equal to E interior. Again, here, like I've mentioned this before, if you want to prove that two things are equal, you want to prove inclusion in both directions. A lot of times, you might have the gut reaction where you want to just have this equals something else equals something else equals something else equals what you want. So like maybe you'd have E equals something else equals E interior. There might be a proof that looks like that, but usually it's quicker if you just go through a proof where you prove inclusion in both directions. But anyway, we've proven that if E interior equals E, then E is open, and we've proven that if E is open, then E is equal to E interior, and so we've proven that these two things are equivalent, and so we are done. Okay, so now let's move on to C. Actually, to make these a little more clear, let's underline them. Okay, so what do we want to do here? So we want to prove that if you have a set E and you have an open subset G of E, then this open subset G is contained in the interior of E. So what we're going to do is suppose G is an open subset of any set E. Then every X in G is contained in a neighborhood which itself is entirely contained in G, which is a subset of E. So the fact that every element of G is contained in a neighborhood entirely contained in G, that's what it means to be an interior point. And you know that X is an interior point of G because G is open. So anyways, G is contained in a neighborhood entirely contained in G. And G is contained in E, so every X in G is contained in a neighborhood entirely contained in E, which is what it means to say that X is an interior point of E, meaning that X is in the interior of E. And this holds for every single element X in G, and hence, G is actually contained in the complement of E. And so in this sense, you sort of interpret this as meaning that that the interior of E is the largest open set contained in E. Because obviously the interior of E is an open set which is contained in E, and any other open set which is contained in E is also contained in E interior. And you can also prove that, like, if you take the union of all open sets contained in E, then that union is equal to the interior of E. So that's another way of proving that E interior is the largest open set contained in E. And that's sort of similar to how the closure of E is the smallest closed set containing E. And so you might think, okay, maybe there's some relationship between the interior and the closure, and it turns out there is, and that's what we're going to prove in Part D. Part D, what we want to prove is that, I'll write it here, we must prove that if you take the interior and then the complement, that's the same as taking the complement and then the closure. So the way that here, I'll prove this first and then I'll ramble about it. Okay. So how do we prove this? Again, we want to do by inclusion. To prove inclusion in this direction, i.e. to prove that the complement of the interior is contained in the closure of the complement, suppose that you choose an element x which is in E interior complement, which is to say that x is not contained in E interior. We want to prove that x is contained in the closure of the complement. Okay, so if x is not in the interior of E, it might be an E complement, but it might also be in E, and just not the part of E that's contained in E interior. So if x happens to be in E complement, then obviously x is going to be in the closure of E complement as well, because E complement is contained in E complement closure. If x is contained in E, but not contained in E interior, which is the only other possibility, then obviously x is not... The fact that x is not in the interior of E means that every neighborhood n of x contains a point not belonging to E. Because if x had a neighborhood, all of whose points did belong to E, then that would mean that x is in the interior of E, which we're assuming is not the case. Okay, so x itself might be in E, or in this case we're saying that x is actually in E, but every neighborhood n of x contains a point not belonging to E. So it contains such a point, so there, that is to say that there is an element y which is in this neighborhood n is not equal to x, and it's also in E complement. This means, if you recall the definition, that x is in fact a limit point of E complement. So if x is a limit point of E complement, that means that x is in the closure of E complement. And so in every single scenario, we have that x belongs to the closure of E complement. And so, hence, and this holds for every single x in E closure complement, and so, hence, E interior complement is contained. I'm going to make the interiors and complements look different. E interior complement is contained in E complement closure. Okay? So, conversely, and now that I'm looking back at it, I think we can just do this. I don't think we even need that sentence that I wrote there, because that's completely... Sure, it's really easy to prove if x is in E complement, but you don't even need that. All we need is that x is not in E interior, and then the entire rest of the proof follows. So yeah. Yeah, then every neighborhood contains a point. Yeah, so there we go. Anytime you can do this is good. Anytime you can accomplish the same goal using fewer details, that's good. Or not necessarily including fewer details, but using fewer logical steps. There's a difference between going into detail in a proof, meaning that you flesh out all the details that you're hiding, and adding in extra steps that are not necessary. Here, what I had done before was I added in more steps that are not necessary. Part of writing a good proof is being able to remove things that are not necessary. You can have a proof that's completely logically sound, but there's other things like this in there that the proof would be just as fine without, and you want to get rid of those because the point one of the main points of math is to like contain as much information, is to portray as much information as you can as efficiently as possible. So if you can portray the same quantity of information using fewer details and fewer steps, that's great. Of course, sometimes you need to go more into details, but yeah. So anyways, I'm going to stop rambling about that. So conversely, I'm going to let, okay, come on, let x, we're pretty close to the end here. Do I have to draw any pictures here? Thankfully not. Okay, so let x be in E complement closure. Then there exists a sequence, we'll call it xn, which is contained in E complement and which does not include the point x, such that xn converges to x. Okay, so every neighborhood of x contains some xn. That's what it means to say that xn converges to x. That means that every neighborhood of x contains at least some xn. And in fact, one of the propositions or theorems that you prove in this chapter is that it will actually have infinitely many elements of xn, because any neighborhood, you can make an infinite sequence of neighborhoods which shrink around the point x, and each one of those has to have an xn, and you get infinitely many elements of the sequence. I'm leaving out some details there, but anyway, so every neighborhood of x contains some xn. But what does this mean? Which means that no neighborhood of x is entirely, okay, we're okay, contained in E. Thus, x is not in E interior, i.e. x is in E interior complement. And this finishes the reverse direction, because this proves that every element of E closure in every element of E complement interior is contained in E interior. No, every element of E complement closure is contained in E interior complement. And so hence we have E interior complement is equal to E closure interior. Now that I'm looking at this, did I just do the same thing forwards and backwards? So x is an E closure complement. This is equivalent to there being a sequence like this. So this is actually if and only if. So x is an E closure complement if and only if there is a sequence in E complement which converges to x, which actually is equivalent to the statement that every neighborhood of x contains some xn. Yeah, I don't know. I think you can make this statement like just entirely bijections. I think you can say that like x is an E interior complement if and only if this, if and only if this, if and only if this, if and only if x is in E complement closure. And again, if you're able to do that, then that's a really nice proof, and that's better than what I've done here. But sometimes figuring out the details of that takes a while, and you don't feel like it, and so you just write this down and you just go with it. So that's what I'm going to do. I'm just going to stick with this, especially since this exercise is continuing to drag on, and we still have 2 more parts. Thankfully, for these, we have quick counterexamples. So, do E and E closure always have the same interior? So, let's see here. Let's look at the rationals. Every neighborhood of every rational number x contains irrationals, and so the interior of the rationals is equal to the empty set. The closure of the rationals will that's equal to R, because every real number is a limit point of a rational sequence, and the fact that R is open in itself, R is an open set in R, implies that the interior of R is R. Hence, in this scenario, we have the rationals, the interior of the rationals is the empty set, which is not equal to R, which is the interior of R, which is, well, R is the closure of the rationals. So the rational numbers gives us an example in which the interior of the set is not equal to the interior of the closure of the set, i.e. here we have the interior of the rationals is not equal to the interior of the closure of the rationals. Okay? So that's the type of example we were looking for. Finally, do E and E interior always have the same closures? Okay, so let E be the set of rationals union with 0, 1. I'm taking the union with 0, 1 here because if I were to take the interior of the rationals, I would again get the empty set, and I don't want to have to worry about the technicalities behind the closure of the empty set. The empty set is weird, and saying something like the closure of the empty set, I don't want to have to worry about that. It is an important thing to know. I just don't know it. So, anyways, I'm just going to use this. So let E be this, and then we have the closure of E. Well, again, E contains the rational, so its closure is all of R. And R is, the real line is not equal to the open interval from 0 to 1. And it turns out that, here, let's do this. So it's actually, the real line is obviously not equal to the closed interval 0 to 1, but this is the closure of the open interval from 0 to 1. And it turns out that the open interval from, wait, what am I doing? E interior is the open interval from 0 to 1. So E interior closure okay, yeah. Right. The open interval from 0 to 1 is the interior of E. And so we can replace this open interval from 0 to 1 here with the interior of E. And we just keep that closure on top. And this is because if you take any interval between, if you take any element between 0 and 1, then you can find a neighborhood which is entirely contained in the open interval from 0 to 1, and so any of those points are going to be in E interior. But if you choose any point which is not in the open interval from 0 to 1, then every neighborhood of that point will contain an irrational number, and so it will not be contained in the interior of E, and thus the interior of E is equal to the open interval from 0 to 1. So again, introducing this open interval from 0 to 1 keeps me from having to worry about the empty set. Okay, so I want to finish this by rambling a little bit about this, because this is really cool. So we have, first of all, note that E complement, remember we said E complement closure equals E closure complement. No, E interior complement equals E complement closure. And so if we take the complement of both sides of this, we get E interior, and remember you take the complement twice and you end up back where you started. So E interior complement is equal to E interior. And so what this is equal to is this is E complement closure complement. So basically taking the interior of the set is the same as taking the complement, then the closure, and then the complement. So we see that you can think of the interior as just another thing that you can obtain by taking interiors or taking closures and complements. The interior is something you can get by taking closures and complements. So you might think, we've seen examples here, like with the rationals, where you take, with the rationals you take the interior, you get the empty set. You take the closure, you get R. You take the interior of the closure, you get R as well. If you start with a set, then if you take the complement and the closure with some number of times, like obviously if you take the complement twice, you end back where you started, and if you take the closure twice, you end up at the closure. Yeah, so how many different sets can you get like this? And it's not obvious at first, and you might play around with examples, and you might find examples where you only get like a couple, but then taking complements. Like here with the rationals, you could take the complement of the rationals and you look at the irrationals. But the interior of the irrationals is empty, and the closure of the irrationals is the entire real line, so that doesn't give you much more. So there you get, if you're starting at the rationals, you get 4 different sets. You have the rationals which you started at. You can take the complement to get the irrationals. You can take the interior to get the empty set, and you can take the closure to get all of R. And if you keep playing around with it, you can't go anywhere else from there. And it turns out, you might think, what's the maximum number of things? And this has been solved. It was solved in 1922, I believe. Which is, especially for for math, that's pretty recent. Like, it takes a long time to start getting to recent discoveries in math. It takes a lot of years and a lot of semesters of work. So according to, what is this? This is called Kuratowski's closure complement problem, which Kuratowski's closure complement problem, that's something that you can go ahead and Google, and you can find a Wikipedia article. By taking closures and complements, need a little more room, you can obtain at most 14 unique sets. From a starting set, of course. So what does this look like? You can find examples online to prove that you can get up to 14. To prove that you can't get more than 14, that's I'm not exactly sure how that goes. But I think what you have is you have E here and you have E complement. So you can take E closure complement, and E closure complement closure. Then you have E complement. No. Oh man, I forget how this goes. But basically what you do is you have this, and you go like 3 to the right and 3 to the left, and then you have an entire bottom row as well. Yeah. Oh, maybe how it is it's like maybe it's E, then over here you have E closure interior, and E closure interior closure, and then here you have E interior. Here you have E interior closure, and then here you have E interior closure interior, and you get like different sets you get 7 different sets on top, and then you take the complement and you get 7 different sets on the bottom, and all of these 7 sets on the bottom are different from all of the ones on top, and so you end up with 14 unique sets. And then you can prove that if you go from any one of these 14, or in any example you find where you can get 14, if you try to go beyond these, then you can't get anywhere else. You'll just start looping through sets that you've already seen. But yeah, I remember taking my first like point set topology class. So it wasn't actually like real analysis. It was actual just strictly point set topology. It was like a separate class. It wasn't algebraic topology either. We basically just went through like the basics of point set topology. It wasn't like a not everyone in the class, I think, was planning to go on into grad school in mathematics. So it was a little bit easier going. But I remember learning about closures and complements, and being asked like what examples, like how many sets can you possibly get, and I remember trying to look through examples and seeing what I was able to do, and yeah, it turns out the answer is 14. So if you're curious about that, then look into that. I think it's really cool. And this is all, you can find an example of this on the real line. So you basically have all the tools that you need in order to find a good example. You could do this yourself before you look up online for a solution. But even if you don't want to do that, dealing with interiors is very important in analysis. Interiors, closures, complements, the interior especially, this is something that you are going to want to understand to help your understanding of analysis. And hopefully this exercise does a really good job of introducing you to the concept and getting you to start thinking about this. Well, in any case, we've completed this proof and everything, and so we are now done.